Hello, everyone. My name is Jalen Lewis, and welcome to our session, Better Than Bopp, Unlocking Higher Temperatures with Low Loss in Nanolayered Polymer Capacitor Films. Again, my name is Jalen Lewis, and I'm the events manager here at Peak, and I will also be your moderator today. I am joined by Dr. Mike Ponting, the Chief Scientific Officer and one of the co-founders of Peak's Film Technology. Today, he will be diving into fusion demands, market needs, and nanoplex. Before we start, I have just a few housekeeping items. Questions will be answered via the Q&A chat following the session, and the webcast is being recorded. It will be made available following the session for you to rewatch or share with colleagues. This is a monthly series, so please stay tuned for any details regarding our September webinar. Without further ado, I will pass it off to Dr. Mike Ponting to talk about the future in fusion.
Well, hello, everybody, and thanks for joining us here. So I wanted to start off by giving everyone a little bit of background on Peak Nano, what we do, and why it's going to eventually relate to fusion and change how the industry is storing energy. So Peak Nano is a materials development company located here in Cleveland, Ohio. We have two facilities. One where I'm at currently is in Valley View, where we concentrate on extruding nanolayered plastic films we call nanoplex, and we'll get into more of that here in a minute. But it's actually an image of that is shown in the bottom right of the slide, and you can see the film coming off of a roller. So it looks like plastic film. The other facility we have here in Ohio is an optics facility where we manufacture our nanolayered optical gradient index lenses, our GRIN lenses, which are used in night vision goggles and some military applications, which also harness nanoplex, these nanolayered film technology that is the core for what we do here at Peak. But today I'll just be addressing how we use the nanolayers in the dielectric film storage and specifically to meet the needs of fusion. Next slide, please. Thanks, Jalen. So again, I mentioned Nanoplex before, and again, this is our brand of nanolayered plastic films. And you think, okay, what is a nanoplex plastic film encompass? And it encompasses several different things. It looks like saran wrap, or it looks like a Ziploc bag film that you may see in your house. But the difference is in the highly ordered structure that we're able to align molecules on a large scale in processing and harness really unique properties. So the image on the bottom left of the slide is actually a cross section or looking from the side on our plastic film, and you can see hundreds of layers that made up this film that we showed here by scanning electron microscopy. So in a nanoplex film, we can put anywhere between 2 or 100 or 1,000 alternating layers of 2 or more polymer materials stacked on top of each other to render some really interesting properties in the overall film. And those properties are what's going to enable some of these really advanced systems to benefit and change how we work technology like fusion, like EVs, like nanolayered optics. So again, nanoplex is our trade name for the layered films, but really, again, there are millions of or thousands to millions of layers within a nanolayer film, and they're leveraged again across different industries depending on which polymers we layer back and forth. So we have films that we use specifically for dielectrics, for fusion. We have specific films and polymers we use for optical lenses, and different films that we use in space exploration or ballistics or food packaging. And our technology is flexible in that we can change the number of layers and which polymer materials we're layering to get these unique properties. And this is a patented process invented here in the US. I was part of the team that was researching and developing these films back at Case Western and DARPA in the early 2000s and have spun it out into Peak Nano. So again, we're a 100% US-based company making these nanoplex films, and we are looking to make sure the US has a secure supply chain of high-performance materials to enable some of these really exciting applications. And Jalen, if you wouldn't mind, go to the next slide, we can start talking about some of them. So fusion. People hear a lot about fusion, and when you look at all the different companies, and if you're following the news, they're talking about different types of systems. So there's some magnetic confinement systems like tokamaks or stellarators, and then there's interfacial systems, which are like the National Ignition Facility out in California in the US that uses inertial fusion. But all of these different fusion systems combine uh, flavors of hydrogen together into helium to release energy. And they do this through either pulses of energy to fuse the materials together, or by confining the hydrogen materials into a very tiny space via magnetic confinement, and then hitting them with a high pulse of energy and plasma to form the two hydrogens into helium and release a large amount of energy. So there's lots of ways people do it, and we have little cartoon illustrations here and what some of those crazy fusion machines might look like. But there's one common thread between all the different types of fusion that people in the US and internationally in Europe and Japan and China are looking at, is they all require a lot of energy to create even more energy. Um, and that's kind of where our capacitor film technology can come in and play a role in helping these fusion companies achieve their goals. So you may have seen press releases in the news from some of these companies. They're pretty well known: Commonwealth Fusion, Helion, Zap Energy. They're all using different types of fusion, and they've partnered with different commercial um, resources that will end up harnessing the energy or the end users of these systems. So it could be Microsoft for their data centers. It could be the national labs to research um, how oh man, lost it. So how fusion energy will work in nuclear weaponry or also nuclear storage. And when these companies are looking at these fusion partners to develop these reactors, one thing that's unique is that each of the reactors takes a lot of energy storage film to create and store the energy that it's going to then use to bound the hydrogens together into helium. So, for example, Commonwealth, their tokamak reactor, it could require, and this is based on a press release from and information from Commonwealth Fusion and some of their earnings and updates calls. Their pilot scale reactor that would do about 400 megawatts of energy would require up to 250,000 pounds of capacitor film or dielectric energy storage film to operate and run. And that's a small facility that they're looking at building in 2035. And if you go to other companies like Helion, like Pacific Fusion, again, the size of these systems might change a little bit. Helion is a similar size to Commonwealth of 400 megawatt. Pacific Fusion is a little smaller and 100 megawatt, but all of them use a lot of capacitor film, hundreds of thousands to millions of pounds, to store enough energy to enable the fusion reaction to take place and release, 2 to 4 to 10 times the amount of energy from the system that they're putting in. And this demand on capacitor film is something new to the industry, new to the suppliers and the supply chain that's out there right now. And it's something that needs to be addressed and analyzed, and needs new materials to realize the full potential of what they're going to do. And that's what we can look at. So how much film is actually required to help all of these companies build what they're looking for in terms of the reactors? Next slide, please. So when people talk about fusion and they go to build these systems, one question that always comes up in fusion is, how long will it actually take to realize fusion or have a fusion reactor creating energy for the grid? Um, and it's something that we're actually starting to see signs of knowing the answer to that type of question. So you can't build a reactor until you start researching, buying, and assembling the pieces. And we're starting to see, if you trace the dollars, you're starting to see where those dollars are coming from the fusion companies into what we call the supply chain companies, or the suppliers of the materials that will create the fusion reactors that will power the grid, power electric vehicles, power space. And it's increasing as you go through the year. So in 2024, the most recent report that's out, there were $400 million spent by the fusion companies onto supply chain and supply chain related expenditures. So these could be fusion reactor walls, they could be capacitor films, they could be batteries, they could be any number of components that go into building the fusion reactor. And we see these large increases coming as companies are getting closer and closer to building their reactors. So with that increase in spending, and we know that there's been about 12 to $14 billion of private capital invested in fusion, we can say that the day fusion will become a reality is becoming sooner and sooner. And we're getting ready to see what that would mean in terms of full-scale supply chain and specifically for plastic films. Next slide, Jim. So what if we looked at those companies listed on the previous slide that each had a different type of fusion reactor and required different amounts of capacitor film to operate? Just looking at the necessary capacitor film that they would require. So what does that look like for demand on the existing market? Or would the plastic film market have to increase production to satisfy the needs of those fusion companies? And if you start looking at the 16 to 18 companies that we surveyed on their plans for building not only the pilot scale fusion reactors, but then also the full scale fusion systems that will then power grids or data centers, what type of dielectric film demand would you need? It gets staggering pretty quickly. So in the previous table, we talked about, okay, the first pilot scale fusion reactors coming on in around 2030. And you can see in this graph here, if you go to 2030, 2031, you start seeing a small uptick in the demand of specifically capacitor fusion film that the industry would need as it relates to the current demand of every other capacitor film market in the US currently. So if all of these companies are successful, and we'll talk about what all of them being successful means and the likelihood in a little bit, but the ceiling for this, if fusion really takes off, we quickly see by 2038, the demand for capacitor film to support the operation of these fusion systems surpasses the current demand of every other market that is using capacitor film in the US. So are we currently set up and able to produce enough film to hit the ceiling of what the fusion capacity demand for BOPP capacitor film would be? And the answer in the US is no. But let's take a more conservative look and say, well, what happens if half the companies or if 10% of the companies are successful? What's the floor for the fusion demand and what does that look like? That helps us set the industry standard investment and understand how, as a supply chain company making dielectric capacitor film, we can set up to service the industry, what that possible floor and ceiling and demand would look like. Jalen, can you go to the next slide, please? So if we again relook at the fusion capacitor film demand, and warning to you, I changed the y-axis here, so we're down more zoomed in on just what the 7 billion pound limit of the current capacitor film market in the US across all industries would be through 2050. If you start putting now the fusion demand, if you only have 10% of the fusion companies, so if you have 2 fusion companies that are successful in their approach for creating energy, if they go full bore through pilot scale and through full production models, what does their demand for capacitor film look like? And you see it's a lot more modest. So again, you're starting to see an uptick, or the first fusion films come in 2022 or 2032, an increase up to 2050 to nearly 1 billion pounds, which is a staggering amount of capacitor film, actually. And if the fusion industry would realize that 1 billion pounds of film by 2050, it would make it a top 5 consumer of capacitor film in the US. So it would become a top 5 market for capacitor film on the floor, on the low end of demand in relation to the other uses currently for that film. And with that kind of demand at a floor, it's still going to be competing for manufacturing capability against these other markets. And if we look at what the other markets are, and Jalen, if you want to flip to the next slide. Thank you. We can see that fusion will be competing for the same materials as electric vehicles and EV chargers, which use these films to store energy and operate the electric vehicle in the power grid, to both convert energy from power stations onto the grid and also maintain a constant charge or capacity on the power grid. In defense, for things like emails or weaponry, for pulse power kind of applications there, for data centers, for mobile power stations. These are the other markets that fusion will be trying to secure supply um, to operate and kind of find its place. And it's kind of funny, fusion, while needing to take material and capacity from some of these applications, which also are not shrinking by any means. The demand for power grid, the demand for EV, the demand for defense and capacitor films is only increasing at a large rate, as you saw from the previous graph. But as fusion battles for the same kind of film, one of the things that fusion could enable are also additional applications in some of these fields. So it's going to set up for an interesting landscape in the capacitor film market. But if you look at these different uses of the capacitor film and you say, okay, fusion's going to need it, EVs are going to need it. Is it the same film? Are we all making the same oranges, or do some people require apples? Do some people like watermelons or cherries? What do they need for the capacitor film to operate the best in the different systems? And the answer is it's similar film. It's really close. So you can use the same manufacturing technology or film thicknesses for some of these applications. So you're pulling from the same resources. You don't need dedicated fusion capacitor film manufacturing lines or dedicated EV capacitor film manufacturing lines, which is a good thing. But it is kind of interesting that if you look at all these different applications that need capacitor film and will need it on these millions of pounds scale, they all have common asks or requirements that they would like to see to continue to evolve and get higher performance out of whatever market they're in. So to have power grid capacitors last longer and operate in more extreme temperatures, they would love to have a dielectric capacitor film with a higher operating temperature. To make EVs go farther and have a larger range, they would love to have higher energy density. So you can put more energy in the same volume of capacitor and capacitor film and make it lighter. So when you look at these different applications and say, okay, we're going to share some of the dielectric film from fusion with these different industries, or fusion is going to require you to switch over the manufacturing capabilities from some of these different applications. The nice part is they have the same asks and the same North Star development goals. So one thing Peak is working towards is trying to not only just fill a need for volume of capacitor films to enable fusion and energy storage, it's to push the performance of the films and fusion and some of these other applications to higher levels through some of the requirements we see on the right: higher operating temperature, higher energy density, longer lifetime, low loss. Can we make the next generation of dielectric material at volume, at scale, on the time frame these market needs to really hit that performance milestone? And Jalen, if you want to go to the next slide. So that's kind of where our story converges with the dielectric energy needs of the US and the world. So with Peak's ability to nanolayer, we can kind of change the rules or how people have previously built energy storage systems or film capacitors. In the last 50 years, the industry has had an option of, if you want a capacitor for electric vehicles, you can look at the 5, 6, or 7 different polymer materials that people have invented and scaled up on the million to billions of pounds scale and say, okay, BOPP is the best polymer material, has the best mix of properties for electric vehicles. So I'm going to extrude thin films of BOPP and wind it in a capacitor, and that's what I'm going to get. And if you switch over to electric grid and you need something that's a higher temperature, or a higher energy density, maybe you'll move to PEN or Bopp. But really, you have to pick either or. You get one of the flavors. You don't get a twist ice cream cone. You get chocolate or vanilla. And that's kind of limited some of the advances and abilities of industry to really improve the performance of the energy storage markets. So again, with Peak and our nanolayered, our nanoplex formulation, we can start making that twist ice cream cone with the polymer materials that we have available and the ones people have traditionally used and new ones people may have never even thought about using before. Everybody loves Dole Whip at Disney World, so we can make a Dole Whip if you want that, using some of the fancy polymer materials that have been invented in the last couple of years, but maybe haven't been so traditionally used in dielectric energy storage. So you can do things like combine a BOPP and a PPS together in a single nanolayered film for a higher temperature, higher performance, longer lifetime film option. And these will be drop-in films that you can still make capacitors. They'll still fit into the electric vehicles or into the fusion systems to power the lasers or the plasma generators. But their performance will be quite a bit different. So again, getting the higher temperature, getting the longer lifetime, getting more energy out of a smaller volume so you don't have maybe 50 of them, maybe you have 25. So again, that's the goals of what we're doing in Peak Nano, and I'll show you a little bit some of the results we have from doing this nanoplex layering method. Jaylen, can you go to the next slide? Thank you. So one thing that we've been able to introduce are again, the nanoplex material, and I'll call it in two different flavors again. So we have a flavor on the left here that's called, we call it HDC, it's high dielectric constant nanoplex. So it's a material that has about 50 to 60% higher dielectric constant than the traditional material that's used, which is BOPP. It has a higher operating temperature. BOPP usually is operated about 85 C up to about 105 tops before it melts. HDC Nanoplex easily operates at 125 and can exceed that in some applications. So that's one flavor we have, and you can get it in different thicknesses and sizes and lengths and all that kind of fun stuff, just like you can of the normal capacitor film. We also have a flavor of nanoplex film we call LDF, which is low dielectric loss. So this is an ultra low loss equal to the best current dielectric material, BOPP. But again, it operates at a much higher temperature. So you're looking at extending the lifetime of capacitors or avoiding derating some of your materials that go into more extreme conditions. So LDF can operate, again, with similar losses to the industry standard BOPP up to 135 or higher C, and it comes in, again, multiple thicknesses similar to what you get in the state-of-the-art materials. So it's with, changing the polymer materials that we're putting in resin A and B, we can get these different twist cone flavors that people can try in dielectrics. If you go to the next slide. And as Jaylen mentioned, I'm the chief science officer here at Peak, so I love fancy graphs and pictures, but to me it's, show me a data table, put some film in my hand, give me a capacitor, show me that things work, and that's what we've been able to do through some development programs in the last couple of years with the Office of Naval Research and here at Peak internally in developing some of the flavors that we're going to talk about. So here's a table for the high dielectric constant nanoplex material. Again, it's polymer film that looks just like a normal plastic film, can come in the typical thicknesses. We're listing 6 to 14 microns here. You can get rolls that are thousands to tens of thousands of meters long. And then when you start to look at the properties and compare them to the state-of-the-art BOPP, we have two grades of HDC. We look at 3125 and 4125. They come with higher dielectric constant, that's your DK. So 2.2 is the industry standard Bopp. Our HDC can be 3.7 to 4.8. It has similar electrical breakdown, so you can run it under similar voltages. But again, the max temperature of capacitors we've made out of these are exceeding Bopp, and the films themselves, again, go above 125 C without any issue at all. One of the trade-offs you do have, because in real world you do have some trade-offs with materials, are the electrical losses or efficiency of HDC is a little bit lower than Bopp here. It's similar to a PET material, but still with a higher dielectric constant. So you balance that out. But for certain applications, especially some pulse power applications of HDC where it really shines, what you can get by going to the nanoplex material that we make is kind of illustrated to the left of the table there in the capacitor pictures. So these are wound metallized dry capacitors. We made 200 microfarad capacitors out of the same film thickness. And then what you look at is the one on the left there, the BOPP, is about twice the volume, twice the height of an HDC capacitor, which holds the exact same amount of energy. So if you're building if you're building capacitors for an application that requires hundreds or thousands of units, you want to take up the smallest amount of real estate as possible. HDC provides you with a solution you've never had before. Or if you're in aviation or some applications like that, again, when weight and volume are very expensive, um, you have an alternative now that can shrink the size of some of your components that power all of the engines, motors, diagnostics that you have for your different spacecraft or vehicles. So next slide. Oh, you skipped one. Go back. There you go. So LDF. LDF was the other flavor of nanoplex we're talking about, the low dielectric loss. So again, here I'm comparing it in a table, hard numbers against BOPP. And LDF is a little different than the previous version of nanoplex we talked about. And the dielectric constant is similar to BOPP. It's a little higher, about 10% higher, 2.35 to 2.2 for BOPP. Dielectric loss is nearly identical. So it's got the really low DF, the loss there. Breakdown strength is right on par. But again, the big difference here is now you can operate these materials at higher temperature, and it's significantly higher temperature. Again, BOPP, you have to derate if you go up to 105 or cool. LDF is a solid working machine at 135C without any problems, and I'll show you some graphs of electrical performance versus temperature coming up here. But it vastly outperforms BOPP in the temperature there. So for certain applications where you might have a more demanding environment, so maybe you're out in the desert, maybe you're cycling the capacitor very quickly and you have some electrical losses and internal temperature rise in the capacitors, LDF will definitely pull through and give you the performance in the lifetime that you're looking for over BOPP without having to derate and add a whole slew of extra components or oversized capacitors. And again, this material looks just like plastic film. It looks very similar to BOPP. Comes on, meters wide rolls. You can go from, again, 500 meters up to, 10,000. And, we've produced it and we'll show you some testing of LDF here in the next couple slides. Thank you. So again, for LDF, wanted to dig a little bit into some of the temperature performance that I was talking about there. The table's a nice summary, but if you get into some of the dielectric versus temperature data, which is showing here on the left, the dielectric constant as you increase the temperature or the environment that the material is operating at of our LDF, which is the blue line, is much, much more stable as compared to the commercial BOPP, which is the red line in there. So BOPP commercially, if you get to around 80, it starts to veer and you start to lose some of your dielectric storage capability, which will cause your capacitor to get derated. Again, the LDF, the stacking of two different polymer materials together gives you an advantage of being able to stabilize that dielectric constant with temperature in comparison to a single material. And we don't see really a drop similar to what BOPP sees until you get out to about 145C. Again, very similar loss. You have the exact same kind of film thicknesses. The only advantage is now you can run the temperature up a lot higher. And if you look at the graph on the right, the dissipation factor, the losses. So as you're cycling these capacitors, the blue material on the graph, again, the LDF, you see a shift of the data to the right, to the higher temperatures, so you can maintain the low losses well above kind of the ceiling that you get for polypropylene, which is really 120, 125. You start to get significant increase in losses there. We don't see those until you're starting to approach 150C in LDF. So again, it's a thermal reinforcement of the material to maintain property and performance that vastly is improved because of the nanolayering combination of the two different materials. Next slide, please. one other aspect of capacitor film is kind of the conversion of the film into capacitors. It sounds a little funny, um, but you want the material to perform electrically, but you can't have it lose all functionality when it's converted into your device. So you say, okay, well that's kind of strange. What do you mean by that? Well, certain materials can be great dielectrically, but sometimes they have large amounts of shrinkage if you go up to accelerated temperatures. If you think back to, well, man, when I was a kid, I'm going to date myself a little bit. We still had shrinky dinks, um, pieces of plastic you would color or draw, maybe write a note to Santa Claus, and you put them into your oven for 5 minutes and watch them shrink to 1/10 the size, and then you could hang them on the Christmas tree, or you had a little toy to play with. Which is really cool for making an ornament. It's not so great if you wind it into a capacitor film and then have to charge and discharge it, and then you have the material smashing down on itself and breaking your device. So you need certain stability, not just survivability at temperature of the polymer materials. We don't want the material just to not degrade. We need it to also not dimensionally change too much that it would hurt the capacitor functionality. So that's something we've looked at in capacitor devices, and this is film data that kind of shows that. Again, the blue lines here are our LDF nanoplex material. The red lines are commercial BOPP material that we actually perform similar or even a little bit better in terms of dimensional stability at these higher temperatures than BOPP. So as you convert these materials into capacitors, you don't have to worry about as much the shrinkage and the internal stress of the parts. They convert very well and wind very well into materials. And if you're metallizing, you can hold the metallization. You're not shrinking. You're not flaking off the metallization and things like that. Next slide. So with that ability to wind and ability to metallize, we've gone through and kind of made some capacitors out of these LDF materials. And that's what's shown there in the top right. Those are some smaller capacitors, 2.4 microfarad capacitors. And then we also made some larger capacitor devices, some of the pressed bricks that you see on the, well, I guess the bottom left row there. And then some about 50 microfarad parts that are metallized and wound on the right. We've done testing on all of these different capacitors at different operational temperatures, at different curing temperatures, just to make sure that the material is surviving. Again, not just at the film level, but it operates in a capacitor device, and it operates in a way that's, past what BOPP is expected to do. So for example, the capacitor windings, the 2.4 microfarad, the 4-cylinder capacitors in the top that are marked 125, 135, 145, 155. Those are wound LDF capacitors that were cured at different temperatures or conditioned at different temperatures to get the shrinkage down or kind of set, and then electrically run the capacitors through a DC burn-in, which was 1,000 volts at 125 C or 135 C. And we had all the parts pass, and you didn't have any dropout at all of capacitor damage to your capacitor parts after curing for 48 hours or after DC burn-in until you got up to 155 C. And if you see the part at the very right of that picture, you can see on the top flat surface, you can start to see a little bit of cracking in the end spray because of the shrinkage of the part. So these parts are, again, polypropylene replacements that operate a solid 40 degrees higher C than polypropylene could ever do at severe derating. And again, it holds at the larger part sizes as well. So when I always try something new, I want to make sure it works in the parts and the devices that it's doing before I sign up to take any samples or really look at the material. And those are things that we were working quite a bit with the Army and some commercial manufacturers on. So with everything working really well and kind of these materials testing out as strong as they have compared to Bopp, and the demand of not only the fusion market coming up, but the continued increasing demand of data centers, of electrical grid renewal, of EVs, renewables, defense. There is a large need for scaled up and domestic supply of capacitor film in the US. And luckily for Peak, we're located in Ohio, which is right in the heart of the US. and we are looking to move our technology past the small pilot scale into the manufacturing realm through opening our own domestic capacitor manufacturing or capacitor film manufacturing facility here in 2027. So Ohio will be the site of the first U.S. based BOPP or nanoplex capacitor film manufacturing lines in the U.S. One thing we didn't talk about at all is that nearly billion-pound demand that's slated for the U.S. by 2050 is currently supplied 100% by international suppliers. The US, North America, Canada does not make any BOPP capacitor film to service any of the applications that are currently consuming energy storage films. So that's a big risk for both the country and domestic developers and suppliers here in the US. And Peak is working with many of those to kind of start to close that gap. And our first contribution is going to be a 7 million pound a year line here in Ohio to make different flavors of the Nanoplex or BOPP film or HDC film, and kind of control and contribute to the advancement of energy storage and some of those really neat applications that we've talked about here that are in need of higher performance capacitor films. So I think with that, we just have a summary here. And again, I appreciate everyone for hanging on and listening to the webcast here with What's Next. And just reminding you again, Nanoplex is a unique approach to making new kinds of capacitor films. It's real similar in how you make standard energy storage capacitor films. The only kind of twist on it is that you're putting these nanolayers in tens, hundreds, or thousands inside of the thin plastic film. And that has enabled two unique flavors of capacitor film, either low dielectric loss, LDF, or high dielectric constant, HDC, capacitor film to be created, demonstrated, tested, and integrated into some applications here in the US. And it is slated for full scale up and production as the first US-based capacitor film manufacturer starting in 2027 when our equipment is commissioned. So with that, again, I appreciate everyone's attention, and we'll conclude the talk.
All right. Thank you so much, Mike. So throughout this session, we have had a lot of viewers submitting questions, and so we have a couple questions for you. The first question from our viewers is, you mentioned LDF has operating temperatures greater than Bopp and up to around 135 degrees Celsius. Is it possible to push capacitor materials to even higher operating temperatures with Peak's layered nanoplex approach?
I love ambitious people. Yes. So yeah, as I mentioned, one of the main questions we get across the industries that we surveyed for capacitor materials is that push to higher temperatures. Again, the current flavors of plastic materials that are out there, they kind of, for capacitor wound film, kind of fall flat. If you get north of 105 C, you get either very expensive or very hard to find materials. We're currently at Peak working on additional flavors of nanoplex materials, where we're trying to, push that upper limit above the 135, above the 150, where we're kind of sitting right now, and kind of go to 200 C. We've identified some polymer materials, and we're working up the small scale kind of pilot proof of concept trials right now. But we would anticipate, and our goal is to have a full portfolio of these nanoplex films that will be able to achieve temperatures up to 200 C.
All right. Our second question says, the enhanced thermoelectric performance of nanoplex is impressive. However, fusion is trending toward applications that require scaled production on the 100,000 to 1 million pounds of film demand to support operations. Is that possible and economically feasible with nanoplex?
Yeah. Okay. So and I get questions like this quite a bit, because we use the word metamaterial or nanoplex, and immediately that has a connotation for some people of a lab scale technology or a small volume technology. The beauty of the technology platform we have at Peak, this co-extrusion layering technology that enables nanoplex to be created and processed, is a similar technology to what people have been harnessing for 20 or 30 years in food packaging, or for display technology film, or even for the polymer films that go into certain tennis shoes, for retaining air pockets. So this is a technology that is definitely scalable. You can make very large rolls of this material, on the hundreds of meters a second scale, which enables both a lot of material to come out, which will meet some of the needs of fusion in a reasonable time, but also to keep the cost of the product into something that's reasonable for large volumes.
All right, and our last question of this webinar today is how and why did you ever consider the concept of nanolayering nanoplex film as a pathway to realizing higher performance dielectric capacitors to support fusion and energy storage?
Yeah, it is a little bit of a different approach. So it kind of comes, and I touched on this a little bit, in the early part of the talk, that my way back, in my PhD education, I was lucky enough to be at Case Western Reserve, where they were working on this technology in conjunction with, some commercial companies like Dow Chemical, 3M, Nike, and some other people. It was real interesting to see the different application spaces and areas that it was being used at for some of these high performance films. And one of our kind of criteria at Case was, well, where else can we use the material if we use different polymers that aren't currently being investigated, and look for different types of material north stars? Can we find new applications? And dielectrics and energy storage was one of those. And we were lucky enough at Case to, come in contact with DARPA and ONR, and the Army Research Lab, and had some collaborative programs with them to really refine the technology, and not only focus in on kind of what we were doing, but which materials we should use. So it was a real neat effort, that kind of was naturally homegrown at a U.S. research institution, and kind of pushed forward and, promoted through some of the government DoD development arenas, and then commercialized through Peak as we saw an opportunity to really help commercially and leverage this technology if we could get it up to a certain production level to make a difference in applications like, again, grid storage, defense, and fusion. So it was a, finding a new twist on a technology that was used somewhere else.
Well, with that, that will conclude our Better Than Bopp webcast today. If you have any questions that were not answered during the session, we will reach out to you directly with all of those answers. So I want to say thank you to all of our viewers for joining us today, and also a thank you to Dr. Mike Ponting for his talk. If you're interested in joining us again, please pay attention to your inbox, where you will receive the slides and presentation from today, collateral around our discussion and the questions, and information about our next webinar. So if you have any topics that you would like to see, or just want to join us on the next What's Next webcast, please reach out to us at whatsnext@peaknano.com, or if you would like to join us as a panelist. I want to say thank you again for attending, and please stay connected through these following platforms, and we will see you next month.